So, welcome to the Tech Hour on the 2nd of February 2023. And the theme is numbers and digital file cabinets and digital typography. And we have a small audience, but a very good one. It's Doug and Philip. And I'm going to do this in a fairly gentle sort of way. So first of all, I'm going to share some URLs through the chat. They'll arrive in a moment. Here are the URLs. So, we can leave all the mics open. Can I ask if, have you both come across the online encyclopedia of integer sequences before?
Yes.
Yes, I've known about it since 40, 50 years ago, and I recently had an entry added in based on a paper I wrote. So,
you're a contributor. You should be giving this talk.
Neil Sloan should be giving it. No, I don't know.
I'm glad that I didn't invite him, because if he'd shown up, it would have been disappointing. He deserves a much larger audience, even though we have a distinguished one. So I'm going to start by sharing my screen. What is it? Entire screen. Okay, so you should be getting my screen now. And some of it's going to be a bit boring because it's a reflection of what's happening here. Can I make one of you co-hosts so you can omit anybody who comes in? I think Doug could do that.
I guess.
Okay, so you now have all the power that I have. And if somebody comes in, you'll see a notice.
Okay.
So, sorry. Oh, here we go, this will do it. So here's the online encyclopedia of integer sequences. And in case anybody is watching it and doesn't know about it before, we can put in any sequence of numbers. Can we have some numbers, please?
42. 354.
I just asked it to search for 42. I'll get a million results.
Yeah.
354.
758.
Okay. Well, we've got 42,000 results for 42. If we put in 50, we'll presumably get 50,000 results. Let's change. What was this second number?
We found a new sequence, which is a number which rounded gives 1,000 times as many results in the online encyclopedia.
XKD has got an entry of that nature, and he says, why is it that all my sequences get rejected? So let's have another number that's not too big. How about 47? Yeah. 57.
That's fine.
Well, that's taken it down to 12,000. And what we can do is we can add 7, because 7 will give us one result at least. The 7 is in the sequence at the top here, you see. So, doesn't find it, and that's because it's searching for exactly that sequence. So I think there's a way to do it, which I think involves quotation marks, but I might be wrong.
What if you put 7 first?
That will have a different meaning and it might work. If I'm correct, this will work. Yeah. So this is all the sequences that contain 7 and 42 and 57 at least once.
Mm-hmm. So still 10,000.
So this is the sum of the divisors of n, which is going to be a lot of numbers. So here's something you can do, which is you can search for names. So there's 1,400 results with Don Knuth. Should we try Gauss? Gauss should give us a lot of results. Oh, 475. That's not many. Gaussian. Well, that's better. So here's one. Cameron, because Christopher Cameron often comes. So here we get picking up Ken Cameron. So we can find lots of things in it. And here's the history of the online encyclopedia. And I don't need to say anything because Doug knows everything or knows the history. So it's over 50 years old and it's got lots and lots of entries. And it was founded by Neil Sloan as a graduate student on punch cards. And in 1993 or 5 or so, it became an online website. So it is very widely used by a small group of people and a sort of growing group of people, in the sense that it's one of the standard places to put information about sequences. So whenever you find an integer sequence in your work, whenever I do it, I look it up in the online encyclopedia, and I either have a new sequence or I have an existing sequence, and it gives me information about it. So I'd like to...
Ever found a sequence which already exists but is defined in a different way?
Now that's called moonshine, and I'll tell you about that after I've told you my little sequence, because my little sequence is unimportant and I don't want it to be swamped by moonshine. So yes, sometimes you get sequences that are defined in entirely different ways and they appear to coincide. And proving they coincide might or might not be easy. And they might not actually coincide. They might differ in the 100th term.
Yeah.
So what I'm going to do is show you some of my work. And sorry, I don't know if you can read that at all. There's a link to it in the chat. If I zoom it up a bit, can I? No, it's, sorry, this is a bit of an opaque medium. Here we go. Do you see there's a number 1 here? There's a column that goes 3, 1, 4.
Yes.
Okay.
Yeah.
So the number 1 is there because when you add it to 3, you get 4. Here you get the number 2 because when you add it to 4 and 2, you get 8. So what's happening is we're looking for powers of 2 and we're getting some of the parts of power of 2 and we're missing something. So if we go down to 531, we find that and we also add 4, we get 13. So we need to add 3. So I'm doing a calculation based upon earlier calculations, and then I'm finding out what's the shortfall. So first of all, the shortfall is 1, and then it's 2, and then it's 2, I think. Sorry, then it's 3, and then it's 6, and I made a mistake, and then it's 9. So at the beginning of the year, I did a calculation and I got 212,369. And that's going to be the next page. which is, no, we're missing a page. Here I searched for 212369. I'll repeat it just so that you'll see it actually happen. So copy, go to the home page. So that's the so I did a calculation a month ago and came up with the sequence 212369. And the 212 at the beginning is quite useful because most sequences just sort of go positive, negative, positive, negative. They don't sort of dip and then come back up again. This is sort of U-shaped. So we get the first result there is something that meant a lot to me, because GF2, which is in the description, is something that I'm already dealing with in this context. So I can now click on this and open it in a new tab. Here it is. And you can't see it, but at the top, there's a URL for this page. So that URL gives me that sequence, and it gives me lots of information about the sequence. So if I just page through it, you can see we're getting a lot of information from a lot of contributors. So this is a mini paper, if you like, and some of the sequences have even bigger papers. And there are two things I want to point to. The first thing is the Kolakowski sequence, which is quite amusing. And then the second one is further down. Oh yes, this one here, sorry. This one here, which is the minimal number of periodic orbits of periods guaranteed by Tsarkovsky's theorem. And a friend of mine did his PhD on Tsarkovsky's theorem and had no idea that my work was connected to his work through the sequence of numbers. We still haven't figured out why and how it's connected, but they're connected. So that's an example of just how useful the OEIS is, because I did one calculation that took me about 2 hours, I suppose, or 3 by the time I got it correct. And then I looked up and I've identified the sequence, and I have a guide to the literature. I have a guide to the literature, which is almost complete. The one thing it's really missing is a link to my work. That's also part of the literature that should be associated with this sequence. And we'll get to that later, because we're talking about using and contributing to the OEIS, which I've never done. So Doug will tell me about that. And the next thing we've got is this really interesting thing, which is the Kolakowski sequence, which is a sequence of zeros and ones. Are you able to read it on the screen?
Yes.
Okay. So let me make it a bit bigger if I can. Yeah, this will work, even though we're missing some of it. So what I've highlighted so far is the number 1, isn't it? And the next number is 2. So we get 1, 1. So we write down a 1. What have we got now? We've got 2 2s. So we write down a 2. What have we got now? 2 1s. So we write down a 2. What have we got now? A single 2, so we write down a 1. What have we got now? We have a single 1, so we write down a 1. We now have 2 2s, so we write down a 2. Now all this is a bit bonkers, but actually when you follow this process, you get the sequence back again. So this is a run length encoding. So we have the number 1 appearing once, so we write down 1. This contributes 1 to the sequence. This contributes 2 to the sequence. This contributes 2 to the sequence, and this contributes 1 to the sequence. This also contributes 1 to the sequence, and this also contributes 2 to the sequence. And then we contribute 1 to the sequence, and then we contribute 2 to the sequence, and so forth. And it doesn't repeat in any obvious sense, but when we apply this process of run length encoding, we get back the original sequence.
Presumably, that.
Sorry?
Presumably, there's a proof of that.
Yes, yes. Well, actually, it's not. It's the definition of the sequence. The definition of the sequence is that there is this process, and when you apply it to a sequence of 1s and 2s, you get back the same sequence. That's the definition of the sequence. So if you have any sequence of numbers, you can always write down the run length sequence, which is group the numbers together so that all the numbers grouped together have the same value. So if the sequence goes 5, 4, 4, 4, 6, those 4s get grouped together, and you write number 4 repeated 3 times, I think it was, and then you forget the fact that it was number 4. And when we have only 2 numbers, we have to alternate between the numbers for the runs. So we have to have a run of 1s, followed by a run of 2s, followed by a run of 1s, followed by a run of 2s. So if you look at the sequence on the screen, you can see that here is a run of 2s. It's 2 2s in a row, and the one before and after are not 2. And here's a run of 1s surrounded by 2s, and you can't have 3 runs. You can't have 3 1s in a row because of the rules for prevent that happening. That requires a bit of thought. So this is a very peculiar sequence, but it has this property of self-similarity, and it is rather odd. The other odd thing about it is that it's really high up in the ordering of the sequence, and I don't know why it got that honor. The previous sequence will be either all 1s or the counting numbers, I think. So
It's looked like it's moved up with time, though. It used to be something else.
well,
M0190.
yes, that's right. Yes, it's got some history that I don't know. I think these are probably 2 previous incarnations of the online encyclopedia. So,
But it has a whole lot of likes.
likes.
Yeah.
Yeah. So there's that. And without the online encyclopedia, I would have computed my sequence 212369 and not known that it was connected to anything, and particularly not known that it was connected to my friend's PhD thesis on Tsarkovsky's theorem. And I'd have to do a lot of work to do the literature search for this sequence. This has told me exactly what the sequence is. After thinking about it for a bit, I found an obvious proof that it's the right sequence that I found, and it gives me literature on it. And it also gives me a place to put my work so that other people who are interested in the same thing can find my work. So it's this is why I mean it's a social networking site for mathematicians, because in Britain, in England, all the top tailors hang out in Savile Row and all the doctors in Harley Street. And so if you're a good doctor, you want a Harley Street clinic. And if you want a good doctor, you go to Harley Street. So this is a sort of marketplace, if you like, for interesting sequences of numbers. So I'm going to answer Philip's question, which is we can search, not only for sequences, but for words. And I happen to know that moonshine is the thing to search for. And there are 165 results. So I'm going to narrow it down to something I already know. Oh, never mind that. Monster. So Moonshine and Monster give you the Mackay Thompson series for Class 1A of the Monster Group, etc. So the Monster Group is an enormous finite group, absolutely enormous. And it's a rather mysterious object. And the first comment is that changing the first term from 24 to 744 gives the classical J function. And then you go to this one for much more information. So we'll do that. So this is the J function. And I won't say much about this, except we've got Conway and Norton here, Conway of games fame. And the thing is that the proof of this result, that these two sequences coincide, except for the first term, is that it goes via ideas in physics and string theory or something close to that. And Richard Borchard's, who proved this result, got the Fields Medal for it. So this correlation between these enormous numbers, these numbers are enormous. You know, I think that if we Google for this number, we'll only get, this is an absolutely enormous number. And this enormous number appears somewhere else, and it doesn't appear in many other places. It's not like a billion. You expect a billion to appear in many places, but this enormous number is very characteristic, and it cannot be by chance, but you have to prove it. And the proof was quite useful and deep. I'm going to finish my stuff now and hope that questions will take us over. So this is, let's make it a little bit bigger, a search on the OEIS for annotated scanned copy. This one will do. I'll just see what we get here. Oh, this is brilliant. Let's see if we can get this one here. This is a letter from Richard Guy to Neil Sloane from 1971. So this is how it was done in the past. And this is absolutely brilliant. So what's happened is that Richard Guy I had lectures in the Mathematical Institute, St Giles, Oxford, in 1971 when this letter was written. No, it was written before I arrived there as an undergraduate student. And Richard Guy has created a nice, neat table, handwritten, I think with a biro, with diagrams and so forth, and sent it to Neil Sloane. And Neil Sloane has put numbers to identify these things with particular sequences. So that was how the OEIS grew in those days. And having knowledge that these sorts of scans existed, although I didn't realize they were so lovely as this, makes me describe the OEIS as the contents of Neil Sloane's file cabinet. Because that's exactly where that document was placed after it had been dealt with. And it was retrieved from that, presumably at some point, to go into the electronic digital version. Shall we have a look at another one?
Yeah.
Okay, so somebody choose one. This one looks quite scrappy. Let's have this one. sure how to. Sorry, this isn't going as slickly as I'd like. Annotated, yeah. A class of permutations associated with commuting functions, 1967. Annotated and corrected scanned copy. Oh my, this is how, this is, so this is William Boyce, sent to Neil Sloan, 1967, mathematical algorithms. It's been produced on a typewriter. It seems to be a mathematical typewriter because it has mathematical symbols. It deals with Baxter permutations. It's probably not published in any other form. Some of the pages seem to have had paper decay in different ways. Do you see that some pages are white and some pages are grey? And then this is all wrong. And for some reason, this is got a relevance to the online encyclopedia. And at some point, we'll find out where it came from. I'm sorry, I've complete, no. Yes, this is something related to this sequence. And we've got about 8 entries to this sequence. And we seem not to have any more parts of that sequence. We've got so this person did some work, and this is as far as it's gone, and it's been recorded. Here's another document that's been scanned. This is from Bell Laboratories. You think they would be able to use something better than this in 1978, wouldn't you? So this is what we had in Bell Laboratories. And
It's at the top, it's not for publication.
it looks as though it's not for publication. Yeah, it sort of says that.
The letter at the top.
Yeah, cover sheet. Not for publication.
It's not for publication.
Yeah. I mean, for somebody who's interested in the social history of mathematics, how mathematicians communicate and that sort of thing, the sociology of mathematics, that sort of thing, this is a gold mine.
Oh yeah.
And it's exactly what a file cabinet is all about. Winston Churchill used to throw all the correspondence he got after he was finished with it into a tin trunk, and then the tin trunk was archived for future use for anybody that was interested. So when you have an author and his archives go into a library, and people go to those archives to understand the author, this is a similar thing here. It's the file cabinet, and one doesn't know exactly what's going on here, but it's definitely mathematical. And we have this funny business of alternate white pages and shady pages. It's almost as if the paper has got different coatings on different sides. And sort of here, you've got the sands of time creeping in around the edges. So I'm going to stop at that point, or try to stop. I'd not looked at these scans at all before we came here. I just sort of knew this page existed. and there's about 4,000 of them. So the final thing is using and contributing to the OEIS. And whilst it's great that it's there, there's a lot more, from my point of view, that could be done if somebody else would do it. Because I print out pages from the OEIS so I could write my notes on them, which is exactly what Sloan was doing when he was creating the OIES, which he was getting documents from people and writing his notes on them, and then they go in electronically. So I'd like a sort of electronic way of annotating my own part, the part of the OAS that I'm interested in. I'd like to be able to say, have a record saying, I'm interested in this page for this reason. Or if we look at the matroid sequence that I talked about, I'd like to be able to annotate, I'd like to have a copy of the OEIS so I can annotate each sequence that I visit with the reason that I visit it, with the reason that I'm interested in it. So I can collect information that is additional to the stuff that is already in the OEIS. And then from time to time, as it's relevant and important, I can ask it to be added to the OIES. And when you look at it from that point of view, the OIES becomes a cross between a piece of software under version control and a Wikipedia, whose articles are not words in the English language. The title of an article in Wikipedia is a word or a collection of words in the English language. The title, if you like, of an entry in the OIES is a description of a sequence, and more in a certain sense, it's not even the description of the sequence. It should ideally be the sequence itself. You should not have two sequences that actually are identical, appearing in two different places. And in the OIES, when that happens and it's discovered, one of the sequences marked as dead, identical to such and such, dead. Of course, it could happen that two sequences go in and they have all the same terms up to 1,000 by chance, but it hasn't been proved that they're the same. And if that's the case, then you have to put them into separate sequences because it hasn't been proved that they're the same. So I'm going to ask Doug if I can stop sharing.
Sure.
And he might to say something about contributing to the OEIS because he has done it.
Just two comments. First, you said that, if you find a really large number that's in two different sequences, it's never a coincidence, which mathematically I disagree with. It's extremely likely that it's not a coincidence, but you can't demonstrate that it's not a coincidence.
I was wearing my layman's hat.
Yes. And that's kind of like the obverse of Guy's strong law of small numbers, which says that there aren't enough small numbers for all of the uses that we need to put them to. So that's why smaller numbers are going to be in more sequences, basically.
Yeah.
So the other thing I was just going to mention is that Don Knuth has a annual Christmas lecture that's a video that he does at Stanford, and the one just last December was about Baxter permutations and their relationship to tatami mats. So that
to what maps?
Tatami mats. It's a craft where you build rectangles, rectangular mats out of bamboo or some other.
Oh, tatami.
Yeah.
Yeah.
So you've seen his Christmas lecture that it's about the relationship between Baxter permutations and all the possible ways to do a tatami mat for a given rectangle. Anyway, I've known about the OAS since, I found the original. He published a hardbound book called the Handbook of Integer Sequences back in the 70s, I guess. And I found it in a bookstore while I was browsing. And I thought that was a really cool idea. And so I bought a copy, and, so I've known about it since then. And it's kind of obvious that eventually it had to be automated because, well, you know, A, it makes sense to automate it and it's more useful that way. And B, there were so many more and more sequences being reported that I'm sure that Mr. Sloan couldn't keep up very well. You know, now we're up to 350,000 or something, but so basically, you know, there's different kinds of sequences that crop up, and some of them are amusing, like the you know, the numbers in the subway stops in Manhattan, which you started out on there back with, you know, 42 and 57, but then you went to 7, so that blew that. But and then, you know, the sequences everybody knows, like counting numbers or Fibonacci numbers, et cetera. And of course, the Fibonacci numbers crop up in so many different areas of mathematics that, so I have in my own personal philosophical universe, I have a sort of you know, the certain sequences crop up so much because it's sort of like a meta version of Guy's strong law of small numbers. There's only so many sequences available to go around for so many simple sequences to go around for all of our various purposes. So in my case, you know, I've known about it for years, and I happen to have a personal project of enumerating, you know, certain objects that have interesting properties there. So it's basically a combinatorial problem, and combinatorialists are always trying to find closed form solutions, and they're wrangling Mathematica and generating functions and so forth. And so, you know, if you solve a problem with a closed form solution, then for some combinatoric problem, you're going to have presumably a sequence that's parameterized by n or whatever. And so you've discovered this and proved it's true. And that's a paper that probably immediately should be added to the encyclopedia. You know, and then there's generating functions, and their coefficients are another sequence that answers some combinatoric problem. So that goes into it. But then there's also non-closed form solutions where you write computer programs, and the computer program explores with the backtrack algorithm and pruning and all that. You know, how many solutions are there to a particular problem or a particular set of constraints? You know, so it's kind of a graph theory problem or whatever. And so then you get empirical results as to what a sequence is. And that's getting a little more dangerous because you never quite know whether your algorithm or your computer code has a bug in it. And, you know, so in my case, I've been re-implementing my searches over and over again, probably done it 5 or 6 times in the last 40 years with slightly different algorithms or slightly better algorithms or algorithms that have better pruning conditions and so forth. And if it comes up with the exact same sequence every time, all right, so that's you know, with a probability, you know, 0.999%, you're pretty sure you're right. So when I published a paper that included this particular sequence 1.5 years ago, you know, I contacted Neil Sloan, and of course, the first thing he asks properly is, well, how confident are you? You know, because there's no closed form solution, there's no generating function. It's just I have a computer program that has consistently produced the same results over the years. And so, you know, I said I was pretty confident, and that was good enough for him because it's an interesting result. So anyway, so he found us the next slot and you know, and there's URLs for the paper, and then I had to figure out some other areas in the encyclopedia that I thought were related, and so we added some links back and forth between the two entries, and so that's how it works. And you know, there's a bunch of other people besides Neil that work as editors. You know, there's just so many sequences coming in these days, which is sort of weird because as more and more of these arcane sequences come in, it's not clear. I mean, you know, it's not like you want to read this particular encyclopedia. Your eyes would, you know, just There ought to be some measure of how arcane a sequence is, and presumably that would be something like how many links to it there are. Similar to the PageRank algorithm in Google, but in any case, yeah, I mean the online encyclopedia is great, and especially finding. I mean, if you find that your sequence is the same as one that's already in there, that is really strong evidence that there's some mathematical relationship between what you're doing and what somebody else has done. If you find the same really large number in a sequence, that's good evidence that there might be a relationship, but it's not as strong as if the whole sequence were congruent. So what else? I don't know.
Can I talk something about large numbers? Because I have a piece of secret information, which is at some point I built a piece of software that would search the sequences for particular numbers. And it didn't look at anything but the sequence, the data at the top of the page. It just looked at that.
You're saying search the sequences in the encyclopedia?
Yeah. You can download all the sequences. When I say all the sequences, at the top of each page, there's a sequence that there are about 50 numbers, and you can download all of those numbers. And I store them in binary in such a way that I could search them very quickly and very efficiently. And I did something I thought was very clever, which is that every number in the online encyclopedia is given its own number so that you don't have to store really big numbers. So the online encyclopedia of integer sequences has probably got no more than about 40,000 numbers in it. Do you see what I mean? It's got some really big numbers.
I understand.
It's compressed.
Yeah, that's right. So it's a compression algorithm. And if you have a sequence that has a number that is not in the online encyclopedia, the sequence isn't in the online encyclopedia. So you can do that search very, very quickly. We haven't seen this number, so it's not in the sequence. And that told me that a lot of numbers appear only once in the sequence in the online encyclopedia. I don't know how many, but there are a lot of numbers that appear only once.
What's the lowest number that doesn't appear?
I don't know. And when it doesn't appear, we'll have to put it in the online encyclopedia. The other thing is about correctness of algorithms. I think we all know that the floating point bug in the Pentium processor, which led to the recall of all those Pentium processors from Intel, was discovered by a mathematician who was doing floating point calculations and getting the wrong answer. And he tracked it down to a fault in the hardware in the Pentium processor. And the fault in the hardware was that the division has got a lookup table in it. That's the way you do quick division, is use a lookup table to get an approximate answer or something. And they burnt the chip. They created the chip with the wrong lookup table. The lookup table had an error in it, and the floating point arithmetic was wrong as a result. I'm going to stop.
Well, there's not much of a solution to knowing whether bugs exist or not in our automated mechanical universe.
I'm going to, I'm attending online as a very junior participant, a conference week after next on machine-assisted proofs in mathematics. And one of the talks is how to prove a calculation is correct. And the normal way in which you prove a calculation is correct is you have an algorithm, you prove the algorithm is correct, and then you prove the implementation is correct. But in some cases, we do a calculation, but we don't have an algorithm. We just compute the answer on this one particular problem. And in that context, what the person suggests, and I think he may be doing it in practice, and I sort of know a bit about him, and that's the sort of thing he would do, is that in the course of the calculation, you create such information that a proof assistant can be made to prove that the calculation is actually correct on the basis of the theory without knowing the algorithm. The theory says such and such equals such and such, such and such equals such and such. Like an integration problem, you can do it by parts, you can do it by substitution. There's all sorts of ways of integrating. And so if you put in enough working, you can prove that the calculation is correct with the machine, even though you're not using an algorithm. It's similar to sort of collecting numbers together and proving that their sum is such and such. You can do that without having to follow an algorithm. You can just use the basic properties to prove that the thing works without an algorithm being involved. So the whole question of correctness is there's an interplay between mathematicians not trusting computers and computers not trusting mathematicians. If a machine checks your proof, that's an example of a computer not trusting a mathematician.
And what do you do if your proof is entirely visual?
I tell you how that was solved.
If it's entirely visual, first of all, it means it's probably really easy for other mathematicians to figure out whether they agree with you or not. And but with respect to computer assisted, I'm not sure there has to be some kind of encoding from the visual world into the computer world.
I can see from somebody in your background, your graphic background, that's a very important question. And there's a group of French mathematicians, Bourbaki, who solved that problem. They started writing foundations of mathematics, I think it was around the time of the Second World War, and they produced a sequence of volumes. It sort of faded a bit. But in the Bourbaki volumes, they solved that problem by not allowing diagrams.
Do you know what the relationship is between Bourbaki and tech?
Tell me.
Look at Don Knuth's tech book. And at the end of each chapter, he has these various paragraphs that are marked with either one or two road signs with swerves on them.
Yeah.
That's taken from Bourbaki. That was the one image that Bourbaki put in their papers.
Okay. Well, that was okay. So I thank you for telling me that. I sort of half. Yeah.
I don't know that Don has ever mentioned that or shown it, but I noticed it looking at some Bourbaki publications, and then I noticed it in the tech book. So
the road sign.
They're exactly the same image.
Well,
it's not the same, or
well, Don would have made it in Metafont, wouldn't he?
Well, I read somewhere that the only image that the Bourbaki people put in their papers was to mark, difficulty ahead.
Yeah, but they relented at some point. They introduced, and you'll like this, Coxeter diagrams. Coxeter diagrams were introduced because they're an essential part of the theory of Lie groups, and you can't do the theory of Lie groups properly without using Coxeter diagrams. Coxeter's been described as the man who saved geometry, which I think is really
nice. My old boss, Benoit Mandelbrot, his uncle was a member of the Bourbaki group.
Oh.
His uncle Zolom.
Oh, was he an analyst?
I don't know quite what kind of mathematician he was. He was a well-regarded French mathematician who was a member of the Bourbaki group, which is sort of the antithesis of what Mandelbrot's work was all about. But
yeah. Speaking of lack of diagrams, it's a famous book by Dirac about quantum mechanics with no diagrams.
Yeah, I actually looked at a copy of it a couple of days ago. It's got an austere beauty.
But a physics book, practically all physics books have diagrams of some sort. Yeah.
Yeah.
I once heard a talk which not only had no diagrams, I mean, it's just a popular science talk by a cosmologist from Oxford. And he gave a talk. He not only had no diagrams, no pictures, he had no slides at all. He just stood up, no projector, no beamer, and gave his talk, which is extremely rare these days. Almost everyone has at least, a few bullet points or something, right? And probably it's not a coincidence. A book about general relativity, and his talk was sort of a popular expose of that, also has no pictures, no diagrams, which is really rare these days. It's like a movie with no music. Can you think of any off the top of your head?
I can think of one, and it's by Claude Landsman, and it's Shoah. It's a film about interviews with people who went through the Holocaust.
Okay, interview like things, that's different, but a normal movie. There's a film by Hitchcock called The Birds. It has no music, which is really bizarre.
There was a long resistance in photography to color photography, because the point about black and white photography is that you know that you're looking at the photograph, you're not looking at the real thing. And in some sense, that's important. It's important that you should fully appreciate that what you're looking at is a photograph. It's not the thing itself.
Well, it's also probably some other opposition just out of inertia, tradition, and so on.
So you're going to give us a link to your contribution to the OEIS, Doug?
Oh, sure.
That would be nice. We'll go into the chat so we can...
And I've done other enumerations where I haven't submitted the sequences yet, but at some point I probably will.
Gotcha. And there you got a link too to Doug McKenna. So, all right.
So my enumerations are of generalized Hilbert curve motifs that are built from where the paths are built from edges in a grid graph, as opposed to connecting the centers of sequential subsquares, which is how most generalized Hilbert curves are drawn, including all of the ones in my ebook.
You got the Fibonacci numbers there.
That's right. So it turns out that sequence, the numbers in those sequences break down into subclasses, the number of which is a Fibonacci number. So for the first three numbers, 1, 0, 1, those are the Fibonacci numbers are 1, 0, 1, 1. And then for 10,101, that breaks down into 2.
Oh, I see, yeah.
So there's two Fibonacci zipping modes that add up to 1,101, and then the next number there's 3 Fibonacci zipping modes, and on it goes. I've been able to enumerate one of the 5 zipping modes for a 13 by 13 grid graph, but everything else is it takes too long using the algorithms I've got nowadays.
So you don't know the higher entries,
Nope.
but the lower entries, the largest entry there is the sum of 3 Fibonacci numbers.
No, the largest entry there is the sum of 3 numbers, and the number 3 is a Fibonacci number. So the next higher number is going to have 5 numbers that add up to it. And the next higher number is going to be 8.
So I misread.
Yeah.
Yeah, I understand now.
So when you find these self-avoiding paths through a toroidal grid graph that has the property that when you unwrap it, the path is a motif for a space-filling curve, the entire solution space falls into different boundary modes. And
Right.
the number of modes is a Fibonacci number, and what I proved is why it's a Fibonacci number. And it has to do with bit patterns where the 1 bits are self-avoiding, which are called Fibonacci bit patterns. And it's also related to something called the Zeckendorf representation of the integers, which is kind of fun, a fun thing, which uses Fibonacci numbers as the base for binary integers instead of base 2. So anyway, so that was my paper. And then, since it reports the result in both the abstract and the paper, that's good enough to get yourself into the encyclopedia.
Well, that's very nice.
I have another paper that I published some years ago that has a sequence in it, but I've only done that enumeration once, so I probably should do it over again because the sequence is rather peculiar. But maybe
now let me just search for that biggest number of yours. It in the online encyclopedia.
Okay.
We've got one result.
Well, then, all right.
I rest my case.
So far, so good. I'm happy.
I'm named after the Fibonacci numbers, you know.
I don't know.
Yeah. You just haven't noticed. When I say I'm named, I mean the online version of me. My email address is jfine2358.
I get it. Well, all right. So I can do you one better. If you look at my paper, that's the submission date is the last Fibonacci date for quite a while. It was submitted on 8/13/21.
Was that deliberate, Doug?
Yes. Well, it was half deliberate. I had been following that date for a while, and then I actually submitted it a couple of days later, but I asked the editors to adjust it, and they thought that was worth doing. And so
yeah. In the flyer in the article about I put on the website about this, I made a reference to the Shakespeare programming language, which is referenced in the Kolakowski paper, which you might have somewhere.
So I guess in the Shakespeare programming language, it must be possible to spell keywords in different ways in different parts of the program.
Let me bring this up for you. Come on. Yeah. I'll send you the link rather than share the screen.
Okay.
So SPL in the link stands for Shakespeare Programming Language. I haven't followed it through.
Yeah.
But Romeo and Juliet are Act 2, Scene 2. Remember me, let us return to Scene 2. Juliet knows about children. The next children will be different. The line is handled back. So it's a description of the algorithm as a dialogue between Romeo and Juliet. Obviously, if somebody sent you that, you put it in your filing cabinet. You wouldn't want to throw something like that away. On the other hand, you wouldn't publish it in a journal.
Right.
So a filing cabinet is a place where ephemera are preserved. Juliet, recall thy worth. Art thou better than a hound? If not, we must proceed to scene 3. I think it's probably time to be closing, although people are welcome to stay if they want to.
No, I'm going to have to take off. So.
So let me stop the recording. Thank you both. And well, it's been an interesting chat, and 50% of the audience have contributed to the online encyclopedia of integer sequences, and it's not often that you can say that of a talk. So thank you very much, Doug, for rescuing the prestige of the Tech Hour.
You're welcome. Although I'm still a little curious about the relationship to tech and the Tech Hour and all. I mean, it's something we're all interested in, but I tried to, give that one little connection. But was there a plan?
The connection is this: that tech is about communication. Well, a large part of tech is about communication between mathematicians, and the online encyclopedia is about communication of technicians, and it's a socially, collectively organized piece of work that doesn't use tech in any sort of profound way. I think it might use caret for superscript or power, but
no, he tries to keep everything in the encyclopedia, written in ASCII, as far as I know.
Yeah, which is part of tech. I think the online encyclopedia shows the need for a shared digital filing cabinet, something like that. And I'd like my mathematical archives to be in a digital form by the time I depart, because that will give them some chance of permanence that paper may not provide. It'll give me an additional chance of permanence. And an archive is a sort of digital archive is what the online encyclopedia is. So I see it as this is one of the problems that has been solved, but needs to be solved time and time again, because it should not just be one online encyclopedia of integer sequences, but anybody that does work of this sort of nature should have an archive that can be shared in the same way that Neil Sloan has an archive that has been shared. So it started because Neil Sloan created an archive and started sharing it. And that's why I see it as being part of digital typography, because I've enlarged the concept of digital typography in my own mind to include this sort of thing. is the sharing of information through electronic media, the sharing of textual information rather than graphical information through digital media. And the online encyclopedia definitely does that.
Mhm.
And the fact that the media, that the information that is shared can be rendered to a form where it prints nicely on a piece of paper isn't necessarily that important. Searching the online encyclopedia is really powerful.
Yep.
And so that's why I think it's relevant to the tech hour, but perhaps that's why nobody has turned up, because it's nothing to do with typesetting, as if that was the whole purpose of the world.
Well, I once bought a book on Fourier analysis solely because it was the first book on Fourier analysis that I saw where it was really beautifully typeset. And it was a Russian book. And it just made me happy reading it. And most other math books I didn't like. So yeah, I understand that typography is important communicating amongst mathematicians. It certainly, but I'm a visual oriented person, so and I don't understand a lot of math. So anyway, anyway, all right. Well, that's about all I can think of right now. So I'm going to bid you all adieu until another time.